Very good evening all and welcome back friends. Welcome back to live preparation strategy and subject revision series for SSC JEE. In the first part of basic electronics electrical students syllabus, we have discussed something about basic electronics questions like EDC part and analog electronics part, and the syllabus especially we have discussed something about the syllabus. My dear friends, you please try to go through the syllabus of SSC JEE, every subject, and in the subject you go through every subtopic, topic and subtopic. You cannot find digital electronics and control systems. But if you observe last few years of historical data, previous year questions, you can find one or two digital electronics questions and one control systems question. Sir, how can we predict this? Actually, sometimes it may happen as the digital electronics is quite common and basic and simple subject, maybe from the diploma level or maybe for the engineering level. They are not asking the questions from complicated area. If you have touch with the fundamentals of digital electronics subject, that is sufficient to answer these questions. Even I don't encourage the students for the special preparation of digital electronics. Even if you have your diploma or BTech notes, classroom notes, that is sufficient. They are asking very simple and straightforward questions. That too, only one question is found in one paper, and some other paper, another one question is found from digital, and one control system question was found. And control systems, you just go through the basics. Actually, for diploma students, the control system is not included in their syllabus. Only the students who completed their engineering, they might have touch with this control system. The two basic, just up to root locus. The just basic, what is the root locus? Applications part. Which of the following method is using for stability of the system? What is the meaning of stability? Closed loop transfer function, open loop transfer function. These kind of simple things are more than sufficient. And from the digital, whatever the important topics we need to focus. You believe me, my dear friends, whatever the topics that I am going to display, to understand the fundamentals of those topics, you no need more than 2 hours. Just 2 hours is more than sufficient. Okay? Because questions are not like ESC or other public sector or gate level, questions are very simple and straightforward. So today's session is only about digital electronics, simple, what are the important topics from the digital electronics and questions found in the digital electronics. And as per my observation from the given questions in SSC JEE electrical paper, I found one question from number system and one question from number system, one question from logic families, right? One question from logic families. But not only from logic families, logic gates also. Both are almost easy, very simple and closely related. And what are the subtopics again from the number systems, Boolean algebra? Safe side, I have written minimization technique. Boolean algebra and K-map, these two are the powerful minimization concepts or techniques in digital electronics, you know. And as I said, you can expect only 1 mark or 1 question from this particular topic in your SSC JEE, or maybe 0. Keep it in mind, my dear. Coming to the reference books, this is just for formality. For the subject, if you really find a subject is actually taking at least 4 to 5% of weightage, then we can say it is a heavy weight subject. We need to focus on that subject more and more. We need to revise so many topics. We need to go through the back side of textbook questions like that. But for digital, no need. If you have any notes, as I said, you can go through it. But just for formality, R.P. Jain, Anand Kumar and Maurice Mano, these are the best textbooks. You can take any one textbook. If you have Already if you have it, okay, right. Coming to the number systems 1, I have I have separated the number systems into 3 parts just for understanding purpose. Yeah, okay guys, I think now voice is clear, right. Under number systems 1, you better to focus on radix conversions. So how many kinds of radix conversions or how many types of radix conversions are available? First of all, we need to focus on already available standard numbers, okay. For example, if you go through the GATE exam, you can find some questions from unknown radix also, but here standard already available radix is sufficient. How many types of number systems that we have studied? Binary number system base 2, octal number system base 8, decimal number system base 10, and hexadecimal number system. Binary, octal, decimal and hexa. Just you should know conversion of every number system into others. So you please try to categorize whatever the important conversion that we have here. I will try to focus on that particular number system. For example, you try to convert binary to others, like binary to decimal, or otherwise you can start it from the decimal, no problem. You can categorize it. You take decimal to others, better. Decimal to, for example, binary, decimal to octal, and decimal to hexadecimal. And again reverse, binary to decimal, octal to decimal, hexadecimal to decimal. Converting this decimal to others, we need to take the quiescent and remainder. we should divide the number. For example, you take decimal number 12 by 2, you write Q set and reminder, you know the procedure. But for reverse, binary to decimal or octal to decimal or hexadecimal to decimal, procedure is same. We need to follow standard polynomial. Bn minus 1 r power n minus 1 plus Bn minus 2 r power n minus 2, that is a standard polynomial. Just I am giving you the separate and standard modules. In this module, you can find total 6 conversions. Next, octal to hexa and hexa to octal along with the binary. You see guys, binary to octal, binary to hexa, 2 conversions and reverse. 2 plus 2, 4. Octal to hexa, hexa to octal, 2. 4 plus 2, 6. 6 plus 6, 12. We have only 12 types of conversions. That's all. We have only 12 types of conversions. You don't have any other conversions from here. You take randomly any conversion, you can see that as one of the conversion here. Binary to octal we can do in a two-way method. Of course, there are 2 different methods. You can convert binary to decimal and then decimal to octal, lengthy procedure. Simple technique, if you want to convert binary number into octal number, you take the binary number and group every 3 bits of binary number and make it as a single digit. The digit value will be in or digit will be in octal. Simple, you see, 8 2 power 3. 16 2 power 4. Binary to hexa. Take the binary number. Example 0 1 1 0 1 1 0 0 is a binary number. I want to convert it into hexadecimal. How it is possible? Simple. Don't go for binary to decimal and then decimal to hexa. Direct. 16 is equals to 2 power 4. You just group 4 bits at a time. 1100 12. But we are converting it into hexa, so that we should write it as C. Got it or not? 0110 6. You can directly write 6. So answer is 6C base 16. Of course, you can also write it as per the microprocessor subject concern, programming language concern. 6C base 16 can also written as 6CH. H represents hexadecimal number. Like that. Sir, for example, if I want to convert octal to hexa, same procedure. First you go from octal to binary. How, sir? Binary to octal, we are grouping 3 bits into 1 digit. Reverse, 1 digit should ungroup into 3 bits. Here, binary to hexa, 4 bits you are grouping into single digit. Reverse, single digit should be ungrouped into 4 bits in binary. Simple. Okay? Like that, you need to go through that entire, all conversions in just 10 to 15 minutes. You should not spend more time. No need to do hundreds of problems, no need to do highly typical questions as we have done in Genco coaching or engineering services coaching or in GATE coaching. Okay? Right. Now, another part of a number system is data codes. Another part of number system is data codes. There are so many data codes and data conversions we have, but my suggestion is the preparation should be very smart. You should not go for the entire topic of the digital electronics, okay? Very rarely the questions are asking, that too some repeated questions they are selecting them from the engineering services paper. You just try to focus on XS3, BCD, binary coded decimal number, BCD, their properties. Numerical wise, I am giving star marked here, gray code. As it is important, I want to spend some time. I will give you one example. Sir, how the examiner can frame the question on grey codes are? Very simple. They will give you some binary number. They will ask you to convert it into grey code. Or otherwise they may give you grey code. They will ask you original value or original number in the binary. And the procedure is, I would like to give you direct example. For example, I am converting binary number into grey. I am doing binary to grey conversion. 4-bit data, 3-bit data as your wish. B3, B2, B1 and B0. Numbers, you take anything, no problem, 0, 1, 1, something like this. I can't write the rules and regulations before example, okay? We don't have that much of time. Direct, whatever the rules that we need to follow, I will explain the rules along with the solution of this example question. You can directly copy the MSB bit. What is the MSB bit? 0. This is going to be a G3 MSB bit in the grey, right? Capital letter, small letter, no matters, no problem. Next, add every consecutive bits to produce the next bit in the grey. But remember, if you find any carry, you please ignore the carry. So, 0 plus 1, 1. 1 plus 1, 0 with carry, ignore the carry. 1 plus 0 is 1. So, G2, G1 and G0. Sir, what is the reverse conversion, sir? Grey to binary. Reverse conversion is what? Grey to binary. See guys, in order to convert the grey number into the binary number, let me take the grey number first. Procedure is almost same, but slightly the difference you can find there from where we are taking the numbers to do the addition. Okay. So, G3, G2, G1, G0. What are the numbers? 0, 1, 0, 1, binary values. Here also, as usual, we need to drag the MSB bit. Rule number 1 is same. It is going to become like an MSB bit in the binary. It is going to be like B3. But instead of adding adjacent bits, here we need to add diagonal bits. Like this. 0 plus 1, 1. Right? 1 plus 0, 1 plus 0, 1. 1 plus 1, 0 with carry 1, ignore the carry. So, this is B2, B1 and B0. Binary to grey, and we got back our number like 0, 1, 1, 0, 0, 1, 1, 0, like grey to binary. This is the conversion procedure, okay? And properties, unit distance code, there are some properties for the grey code, you need to understand it. You need to go through it. Read any notes, no problem, okay? And third set of number systems is complement numbers, arithmetic operations. We can say arithmetic operations. Complement numbers. Here, what is the use, what is the procedure to do 1's complement and use of 1's complement in arithmetic operations? That is enough. There are so many subtopics involved in this complement numbers for gate and engineering services, but for us Just what is the 1's complement, what is the 2's complement, that's it. How to write 1's complement and 2's complement. How to write 1's complement and 2's complement. 1's complement, if you want to write, just interchange 1's and 0's. But for 2's complements, first you have to take the 1's complement and add 1, right? Just we have to take 1's complement, and if you add 1 at LSB, you will get the 2's complement data, right? During this process, if you get a carry, ignore the carry. During this process, if you get a carry, ignore the carry, right? That is the 2's complement method. So, for example, I cannot explain the entire 2's complement arithmetic operation. You know, the students who already entered into or attended the classes, only 2's complement arithmetic operation concept takes minimum of 1 to 1.5 hours, right? So, that is why I am directly coming to the point. If you find certain number, any number, right, for example, 1011. If you find MSB as 1, you understand this. If you find MSB 1, this is the so and so number. They are asking you to find the value of this number represented in 2's complement. Value of this number which is represented in 2's complement. Represented in 2's complement. So, how to handle this type of questions? You take the MSB. If you find MSB bit 1, you remember, you should recognize that number is a negative number. Most significant bit MSB. If the MSB is 0, you should understand that number is positive. If you recognize 1 at the MSB, you should understand that number is a negative number. If it is a positive number, directly you can convert into decimal. If it is a negative number, first you should apply 2's complement. Don't forget to take negative sign. Apply 2's complement. If it is a negative number, then only you apply 2's complement. Okay? We cannot go for the proof and why we should apply 2's complement only if it is negative. No. Straightforward point. MSB1, you should understand that number is negative, minus sign, and apply 2's complement. If you apply 2's complement on this number, you will get 0101. As per your technique, see 1011. For this, we are applying 1's complement, 0100. Then if you add 1, this is going to be a 2's complement number, right? 1011, so 0100 added 1, so that 01, as I said, you got 0101. So that after 2's complement, direct, after 2's complement, you are going to get 0101. That means, what is the answer? Answer is, don't forget negative sign there, okay? Answer is -5. Like that, you should know the direct 1's and 2's complement conversion. Even sometimes if the examiner provided the number, you must be in a position to find its value in integer form, okay? Right. VSK, Raju, is it clear? Right. Then, Boolean algebra. You no need to go for the complete detailed Boolean algebra, all rules and regulations. Just you should know what is commutative law, associative law, distributive law, De Morgan's theorem, that's all. Like example, right? For example, De Morgan's theorem. A dot B whole bar, you can adjust it as A bar plus B bar. A plus B whole bar, we can write it as A bar dot B bar. We can prove it by using perfect induction method. It means take ones and zeros, left side and right side. LHS value will be same as RHS. But whenever we need to use these kind of things in the minimization and logic gates concepts, there you can understand the real importance of De Morgan's theorem. Okay? And another important one is redundant literal rule. According to this, A plus A bar B can be written as A plus B. Whatever you do, but you remember it. I don't know what you guys will do, prepare or practice or read whatever, but compulsory you have to remember this. Similarly, another form, A bar plus A B bar is equals to A bar plus B bar, right? A bar plus A B bar is equals to A bar plus B bar. And along with the Boolean algebra, just try to have a look over K-map, Carnot map, K-map minimization. No way to frame the questions on this, but just for safe side. If you find 4 adjacent cells, quad, we can group it, take the common terms. Octave, 8 min terms, adjacent terms, you can group them. Folding is possible in K-map, folding is possible, but remember offset and diagonal grouping is invalid. I think you may not, it is not able to see properly. You see, for example, if you find adjacent cells, you can group them, but you cannot group this. Diagonals are not allowed into grouping. Like that, you please go through the basic rules of K-map. If you find a K-map, you must be in a position to answer it, minimize it, that's all. And logic gates. We have totally 7 types of logic gates. We have totally 7 types of logic gates: NOT gate, AND gate, OR gate. These 3 gates are called as basic gates. NAND NOR, universal gates. NAND and NOR gates are called as what? Universal gates. And another 2 gates are derived gates, are also called as arithmetic gates and very powerful gates, exclusive OR and exclusive NOR gates. We can implement all these logic gates. How we are implementing these logic gates? Internally with the circuit. We can implement them by using bipolar junction transistor or by using MOSFET. Even diodes also. Some of the logic gates can implement by using diodes also. Right. Basic gates. NOT gate, AND gate and OR gate. These are the basic gates. What are the notations? We can call them as operators. Operators of these logic gates. They are asking about the operator symbol. Very simple questions. But if you don't have an idea, definitely we will confuse. Operator symbol for OR gate is plus. Everyone knows this. Operator symbol for AND gate is dot. Also, no. Everyone knows this. But we will generally people underestimate them. Can you guess what is the operator symbol of NOT gate? Operator symbol of AND gate is dot. Operator symbol of OR gate is plus. Okay. What is the operator symbol of NOT gate? The operator symbol of NOT gate is exclamation mark. We call it as what? Exclamation mark. Okay. And you know well, this is a IEEE standard symbol of NOT gate. This is a IEEE standard symbol of AND gate. This is a IEEE standard symbol of OR gate. A bar, AB, A dot B, AB, A plus B. And derived gates, very important, okay. What are the derived gates? Exclusive OR gate and exclusive NOR gate are called as derived gates. These gates are also called as arithmetic gates. These are also called as arithmetic gates, remember. Which of the following gate is used for arithmetic operations mainly, main role? Or magnitude comparator. For these kind of questions, blindly we can select XOR, XNOR. They will give you only one, either XOR or XNOR. This is a symbolic representation of XOR gate. Let us say A, B are the excitations. What is a Boolean expression for XOR? A bar B plus AB bar. Coming to the truth table, AB, we can write it as A XOR B notation. You must take all possible combinations at the input. Similarly, exclusive NOR gate, just it is a complement of XOR gate. That's why we will have XOR gate symbol only, but XOR operation whole bar complement, bubble represents that complement. After complementing this A bar B plus AB bar, we will get AB plus A bar B bar. AB and A XNOR B. 0, 0, you should take all possible combinations, 0, 0 to 1, 1. What is the output? Substitute A0, B0, output is 0. A0, 0 bar 1 into B value 1. So, 1 and this is 1, you get 0 here. 0 bar, 1 into 1, 1, 1 plus anything 1. So, that this is 1, 0, 0, substitute 1 into 1, 1, 1 plus 0, 1 plus anything 1. Both are just complemented to each other. 3 input, 4 input, if number of inputs increases, rules are completely different. I repeat, for 3 input XOR XNOR, rules are different. There are so many rules will come. How we are connecting and how we are obtaining them will decide it. I am only talking about 2 input XOR XNOR. I repeat, my dear, I am talking about what? 2 input XOR XNOR. This is sufficient for us actually. This 2 input XOR gate producing 1 for odd number of 1s at the input. That's why we can also call it as OD gate. OD gate. More than 2, completely story is different, okay. Immediately I can write 1 or 2 bits, but it makes more and more confusion. Whatever the required thing we have, on that we better to focus. For even number of 1s, output is 1, 2 1s, output 1. Sir, but here this is also 1, no 1s, 0 1s, no 1s means 0 1s, 0 is a even number. It is a coincident gate, also called as even gate, only for this case. Only for 2 input XNOR gate, okay, not for more than 2 input, right. But truth table is very, very important. Truth table and the binary expression, that's enough, right. This is something about XOR XNOR gates, and their operations are very, very important. You must go through their operations also. PDF, I will try, dear. Who is this? Mukesh Kumar. I will try, dear. I will try to upload. And universal gates. What are the universal gates? NAND and NOR. By using only NAND or only NOR, we can implement any other logic gate. That's why we are calling them as universal gates. I will focus on only NAND gate. I repeat here, I am just focusing on NAND gates. Rules, there are level 1, level 2, level 3, level 4 questions, and for level 1, level 2 we have rules and regulations, and there are lot of things, but I will give you one table. I hope that may be sufficient for you. Okay. For example, NAND gate. What is a NAND gate and its truth table? First of all, you see, you know, this is a NAND gate, basic IEEE symbol. Output is AND plus NOT operation. Okay, that's all. Now coming to this, you don't ask me, sir, how did you get it? These are the standard circuits. We have rules and regulations, proof is there, but no need of proof. This is a standard circuit of inverter by using NAND gate. Just AND operation and then bubble, NOT operation. A dot A, output is A bar. Input A, output A bar. It is a operation of a NOT gate. Next, this is a NAND gate. Output is what? AB bar. If I take this NOT gate here, this complement NOT operation, complement get cancelled, output is simply AB. What does it mean? AND gate can implement by using two NAND gates. Let me take two inverters. Excitations are AB. This is A bar, B bar. What is output? A bar dot B bar whole bar. Apply De Morgan's A double bar plus B double bar. That means A plus B will come. So, NOT gate or inverter, you can write it as inverter. AND gate, OR gate. Now, see guys, let me take one simple and standard structure of a NAND gate for XOR and XNOR. To obtain this circuit, actually we have some methods and procedure, but actually no need. All are NAND gates. Excitations are AB. This is AB bar. Okay, AB bar. If you write the expression here, A dot AB bar whole bar. If you apply De Morgan's, A bar plus AB will come. So, this is A bar plus AB and this is B bar plus BA or B bar plus AB. After simplification, here if you simplify it, A bar plus AB dot B bar plus AB. Don't forget this bubble, whole bar, right? So, you see, this is A bar plus AB double bar, that's why I wrote directly AB, okay, please. Now if you apply again similarly one De Morgan's theorem here, you will get A plus, A dot, okay, A dot AB whole bar. If you, or otherwise you can write another step. Due to lack of space, I am trying to skip one step, but no problem, I can adjust it. First you apply De Morgan's on this line. This time you need to apply De Morgan's for 2 times separately, okay. A bar plus AB whole bar plus will come B bar plus AB whole bar. Now I can't write again De Morgan's, I am taking direct step. A double bar dot AB bar. AB bar means what? A bar plus B bar. That I am going to write directly. Similarly plus B dot A bar plus B bar. A into A bar 0. Result is AB bar. B into B bar 0. Result is A bar B. A B bar plus A bar B means what? A B bar plus A bar B is nothing but XOR gate. So, here the expression is A XOR B. Then what is the complement of XOR gate? XNOR. Another NOT gate using NAND will give you XNOR. But here they don't ask you the proof, relations and all, they are simply asking you number. Minimum number of NAND gates required to implement a NOT gate 1, AND gate 2, OR gate 3, XOR gate 4, XNOR gate 5. Similarly, number of NOR gates required. This table can definitely help you. Number of NAND gates to implement one NOT gate 1. Even NOR gates also 1 for the NOT gate implementation. Now onwards numbers will be different. You know already from this screen, we need 2 NAND gates for AND operation, 3 NAND gates for OR operation, 4 NAND gates for XOR operation and 5 NAND gates for XNOR operation. Here no need of proof, you try to, first I will write the numbers, then you will get some, definitely something will triggers you, how to memorize the table. Actually for NOR operation we need, AND operation we need 3 NOR gates, but only 2 NOR gates for OR operation. That means what? Numbers are reversed for AND and OR. In case of NOR gate, similarly here also 5 and 4, right? After this level 2, level 3 will come, but level 2, to start the level 2 and level 3, dash and compensation type and bubble and compensation type or graphical model, there are different methods. Even at least we need to spend minimum 40 minutes for each method. Otherwise it will create unnecessary confusions. But I don't expect the question up to that level. The standard table based questions more than sufficient for us, okay. So at least you can remember like this, say 3 and 3 and 5 and 5, right. So this is some basic information, right, from NAND and NOR gates. And logic families, there are 2 types here, saturated logic and unsaturated logic families. Unsaturated. Under saturated logic families we have diode transistor logic, transistor logic, high threshold logic, integrated injection logic, I square L, IIL, okay, NMOS logic, PMOS logic, CMOS logic. Under unsaturated logic, we have 2 types, Schottky TTL and ECL. ECL stands for emitter coupled logic. Now, I can't explain each and every circuit, but main points, main important points, even you can go through the ECE engineering services paper, you can find these questions directly. Which of the following logic family is having highest threshold, highest noise margin? If you find the question about noise margin, NM, high noise margin, HTL, high threshold logic. Which of the following logic is very popular up to MSI, medium scale integration? Very popular, that is TTL, medium scale integration wise. Which of the following logic dissipates very less power among all? Less power, CMOS. Like that we have some special logic families with some special specifications, okay? Power dissipation is very, very less. That's why CMOS is more popular. And IC fabrication, we are using IIL, integrated injection logic, and for VLSI level, we are using CMOS. And for IC fabrication, package density is more. Which of the following logic family is having very good package density? CMOS is the answer. Among all logic families, which of the logic family is the fastest logic family? High speed. Schottky and ECL both are high speed, okay? But if you find both, you should select it, high speed. High speed are fastest. Both are, actually both are fastest. They are not giving Schottky, so ECL, they will definitely give you ECL. And here drawback of this entire logic family is more power dissipation, you remember, okay? Like this, they are asking simple questions. No need to do research on logic families by taking circuits, writing KVL, KCL, writing fan in, fan out, noise margin calculations, nothing, no need. For our exam, preparation style should be different, okay? You should do some smart work. No need of doing hard work, right? One example question, I will see. Try this. See guys, the hexadecimal representation of some number is given, that is in octal. He is asking in hexadecimal. First you take this octal number, convert it into binary. What I told you, 8 equals to 2 power 3. So ungroup every digit into 3 bits in binary, 3 bits. 100, 4. 0 means 000. You should use 3 digits compulsory. 7, 111. What is this? Binary. What do you want? Hexa. Now convert it into hexa by grouping 4. Why sir? Why? Because hexa means, what is the base value? 16. 16 is equals to 2 power 4. We need to group 4 bits from the binary. Okay? From right side, 1, 2, 3, 4. 1, 2, 3, 4. 0, this is 7. But sir, what about this sir? Single one? Yes. You have to pad with zeros. If there is a shortage, you take zeros on left side, no problem. That means it is going to be 1. 107, what is the base number? 16. 107 base 16. A is a correct option. Okay. Output of a NOR gate is high if NOR gate, what is the expression for NOR gate? A plus B whole bar, R plus naught. Output should be high. When that output will be high? If inputs are 0 plus 0, 0, 0 whole bar, 1. Any of the input is 1, 1 plus anything 1, 1 bar 0 will get at output. Output is high only if both the inputs are 0, 0. All inputs are high, all inputs are low, all inputs are low. D is the correct option, right? D is the correct option. No one responding? Yes. Okay guys, and I will try to take the PPT, this PPT into PDF, and our team will respond you how to get this PDF, right? And this is the syllabus of digital electronics only for the SSC JEE electrical paper. Whatever the syllabus I have shown, please don't go for the topics beyond this. These are more than sufficient. Let me show you the topics again. Better to go through this topic. No need of combinational circuits, sequential circuits, and remaining all topics. If you are already good, happy. Otherwise, these are the topics. It is extra interest behalf of ACE Academy. For the students, at least they should not miss even 1 mark also. In fact, digital electronics is not there in your SSC JEE electrical paper syllabus up to 2023. Okay? Maybe next year, if no one knows, they may include, but as of now, no information. Right? All the best, my dear friends.